In this video, we talk about logarithmic derivatives and branches, and then some identities of the logarithmic function. We start by identifying the logarithmic function of a complex number, and we had derived that in a previous video, that log of z would be equal to log, and then writing the z in exponential form, r e to the I theta, is equal to natural log of r plus I theta plus I 2 pi n. And because of this I 2 pi n, we see that this is multi-valued. In other words, for one z, we can have multiple values because of this theta. The theta is equal when we go around 2 pi radians. So what we defined so that we could have a function is this capital log of z, which is equal to natural log of r plus I theta, where n is equal to 0. And this is a single valued function. Then for the purposes of deriving a formula for derivatives, we write this form, this natural log r plus I theta, equal to we separate out the real portion and the imaginary portion. So it's u r of theta, that will give us the real portion, plus I v of r theta. So in this case, u of r theta would be equal to natural log of r, because this is the real portion, and then our v of r theta is equal to theta, because that's what gets multiplied by I, and because becomes our imaginary portion. So we will derive this formula here, which is the derivative of log of z, and we have some of the outline here, and at the very end we see it's equal to 1 over z, which is nice because it's consistent with what we know for real numbers. But there's a few calculations in here which we will do in the video. And the two things we had to do in order to take this derivative was, first, we had to define a branch so that this was a single value for log z. And we'll talk about what a branch is. And then second, we looked to see that then our function, our log z function, satisfies conditions for differentiability. And we put this in polar coordinates. Our function f of z is equal to, again, the real portion, which is dependent on r and theta, plus I plus the imaginary portion, which would be equal to theta. And we said that it has to be defined on some neighborhood at a point z naught, which is equal to r naught plus I theta naught. And to be differentiable, first, the first order partial derivatives of the functions u and v with respect to r and theta had to exist everywhere in the neighborhood of z naught. And second, those partial derivatives are continuous at r naught theta naught and satisfy the Cauchy-Reimann equations that we have from a chapter 2 video. And the Cauchy-Reimann equations, for review, is equal to r partial derivative of u with respect to r is equal to v partial derivative with respect to theta, and that u partial derivative with respect to theta is equal to minus r v partial derivative with respect to r at the point r naught theta naught. If these two conditions are met, then we can find the derivative at z naught, and its value is equal to e to the minus I theta partial derivative of u of r plus I partial derivative of v with respect to r. So here is how we derived this formula. Then, because we used a branch, we go ahead and talk more about branches. So essentially the logarithmic function, because it's periodic, is a multi-valued function, but we can get a single value and continuous domain, an analytic function, if we made a cut at the ray theta equals alpha. So this is what this diagram here is. We're in the complex plane, and at some angle alpha, we make this cut, which is this line that goes from the origin out. So a branch of a multiple value function f, again, this is like a little, our multi-valued function is with the lowercase f, just like our log z is with the lowercase l. And if we want to branch, it's a single valued function, capital F, the way this log also has a capital L, that is analytic at some domain at each point of z, which the value f of z is one of the values of f. So in other words, for any particular value, instead of having these multiple values, we choose one, and we choose it based on this branch. And so the principal branch of the logarithmic function is log z is equal to natural log of r plus I theta, where r is greater than 0 and theta is between negative pi and pi. And you notice here that pi is not, the line theta equals pi is not included. So for logarithm, I can draw my branch cut on this graph here. So it's at theta equals pi, or theta equals negative pi, right? It's negative pi if you're looking this way, it's pi if you're looking this way. So my values of theta then can go from negative pi all the way to pi, not including pi. So this blue line here is my branch cut. That's where I cut off the values that are allowable for my theta. We have a branch cut is a portion of a line or curve that is introduced in order to define a branch of a multiple value function f. Points on a branch cut of f are singular points of f, and any point that is in common to all branch cuts of f is called a branch point. The branch cut for the principal branch of the logarithm consists of the ray theta equals pi, and we'll go over more of these ideas with examples. Once we've gone through the topics of logarithmic functions, derivatives of logarithmic functions, branches and principal branch, and this other surprising fact or lack of identity here, we will go through some identities of logarithms. Now we're going to back up and we're going to look closer at the derivatives of our logarithms. To review really briefly, what we talked about in our last video was developing the formula for the logarithmic function of a complex number. And when we developed that formula, we really wanted the log to be the inverse of the exponent, so that log e to the z would give us z. And this is true for real numbers. But what we found for complex numbers, that we got log e to the z, the inverse would be equal to, or to appropriately define log, so it was the inverse of e to the z, we got that's equal to z plus I to the 2 pi n. So we got this extra stuff here. And that is what made it a multi-valued function. And the extra stuff comes from the fact that e to the z is a periodic function. And then also another form of this equation, which we saw in the last video, is equal to natural log of r plus I theta plus 2 pi n. And this is, this should have an I in front. And this is the form that we normally use when we write our solution for log, this one here, which is why it's the one written up here. And what we said, this is multi-valued, and then in order to make it a single-valued function, which is important when we want to take derivatives, we set n equals to 0, and we get this principal log value right here, which is equal to natural log of r plus I theta. For this video, we also write this log formula that is written here, natural log of r plus I theta. We separate it out so that we separate the function of r theta that gives us the real portion of our log function, right? So natural log of r is a real number. R is a radius, it's a real number. Natural log of the real number is just the real number. And then we have I times theta. So this theta here is a function of r and theta, and it gives us the imaginary portion. It gives us the y portion of our log. And we write it this way so that later we can confirm using the Cauchy-Reimann equations that the log is something that we can take the derivative of, and then two, the Cauchy-Reimann equations will tell us what the derivative is. And so here, this portion here is rewritten. I added this on for this video. So this is equal to u of r theta plus I v of r theta, where u of r theta is equal to natural log of r, the real portion, and v of r theta is equal to theta, which is the part that gets multiplied by I to be the imaginary portion. So first, to derive the formula of the derivative, we have to define a branch. And for the branch, we're going to choose the principal branch. Then we need to verify that log z is indeed differentiable. So we will use the ideas from our Chapter 2 video about sufficient conditions for differentiability, which I have copied here for your reference. And it says if we write f of z in the form u of r theta, the real portion, plus I v of r theta, and that the function is defined throughout some epsilon neighborhood of a point z naught, which is equal to r naught e to the I theta naught, if the three conditions are met. First, the first order partial derivatives of the function u and v with respect to r and theta exist everywhere in the neighborhood. That's the first condition. And second, those partial derivatives are continuous. And third, the partial derivatives satisfy the Cauchy-Reimann equations, then we know that the derivative f prime of z naught exists, and we have a formula for f prime of z naught equals e to the minus I theta u partial derivative of u with respect to r plus I partial derivative of v with respect to r. For our logarithmic function, u of r theta is equal to natural log of r, and v of r theta is equal to theta. So the conditions we need to check to see that it is differentiable, and this is what this theorem tells us. It tells us for any complex function, and we're going to use this theorem to verify the logarithmic complex function is differentiable. So the first thing we need to do is see that the first order partial derivatives of the function u and v with respect to r and theta exist everywhere in the neighborhood. So here we have u of r theta is equal to natural log of r. So the partial derivative of this function with respect to r, so the derivative of natural log of r with respect to r is 1 over r. The partial derivative with respect to theta is equal to 0 because there's no theta terms. Here the partial derivative with respect to r is 0. The partial derivative with respect to theta is equal to 1. The next thing we need to know to prove that our function is differentiable is that, one, the partial derivatives are continuous, which these functions are continuous, except this is not continuous at r equals 0, but that's okay because 0 is not part of our branch cut. Remember, we're looking at, we define a branch, and we'll talk about this more, why 0 is not in there. But these are all continuous on in the space we're looking at, and they satisfy the Cauchy-Reimann equations. R times partial derivative of u with respect to r equals v, partial derivative of v with respect to theta, and u of theta is equal to negative r, v of r. So let's look at that for our logarithmic function. So we look at r times ur. So we have r times, and we already calculated ur is 1 over r is equal to 1, which we can see is equal to v theta. So this first condition is met. And now we look at u of theta, which is equal to 0, which is equal to negative r times 0, which is equal to negative r times vr. So this second condition is met. So the Cauchy-Reimann conditions are met. So now we see that we have sufficient conditions for differentiability. So we can differentiate log of z. Finally, the last part of our theorem tells us how to find f prime of z. And again, this function, this derivative equation was derived in a chapter 2 video. So f prime of z is equal to e to the minus I theta partial derivative of u with respect to r plus I partial derivative with respect to v with respect to r. So we have partial u with respect to r is 1 over r, partial of r with respect to, v with respect to r is 0. So I have e to the minus I theta 1 over r plus I times 0, which is equal to 1 over r, and then I'm just going to move my e to the I theta on the bottom, and this should be a plus, which is equal to 1 over z. And so that is our formula here for the derivative of log of z, and we have verified it's just like our real numbers, it'll be 1 over z. In my overview slide, I tried to put some of the key steps here in our derivation of the formula. But of course, this part, you have to know what you're doing and use this theorem here that has the Cauchy-Reimann equations, and then the final function f prime of z naught. So the next topic we're going to look at is branches of logarithms. The idea of a branch is that the logarithmic function, because it's periodic, is a multi-valued function. There are other functions that are similar to periodic and multi-valued. Logarithm is one example. So the idea is we don't want a multi-valued function, but we can get a single-valued function and a continuous domain and an analytic function if we make a cut at the ray theta equals alpha. So for here's our ray, theta equals alpha, and we're only going to consider the values of theta between alpha here and alpha plus 2 pi. And then we stop. We do not cross this line here. So we don't say, oh, now we can add another 2 pi because then we're going to be crossing this line. We're only considering theta between alpha and alpha plus 2 pi. And whatever this alpha is, that's considered our where we make our branch cut. And it's important to know where your branch cut is. A different value of alpha will give you a different branch of your logarithm, right? So one branch gives you certain values for your logarithm. If you have another branch, you can potentially have different values for your logarithms. And here we say that a branch of a multiple value function, so is little f. So our multi-valued function, little f, is like the log of z, where we have the natural log of r plus I theta plus I 2 pi n. So that's our little f of z. And the branch is a single valued function, capital F. That's like this capital F here, where we have the branch where n is equal to 0, natural log of r plus I theta. So it is analytic in some domain at each point z, in which the value of f of z is one of the values for little f. This last statement here, that f is one of the values of little f, for example, if z is equal to the complex number 2 e to the I pi over 4, then f of z looks like natural log of 2 I pi over 4 plus I 2 pi n. So some of the values for this multi-valued function is natural log of 2 plus I pi over 4, natural log of 2 plus I pi over 4 plus 2 pi, natural log of 2 plus I pi over 4 plus 4 pi, and then you have plus 6 pi, plus 8 pi, etc. There are many values, whereas this single valued function, this branch, when we choose a branch, then we have f of z, I'm sorry, this should be z, is equal to natural log of 2 plus I pi over 4. So it just picks one value. A different branch, let's say f2 of z, might choose the I pi over 4 plus 2 pi n values. And for the logarithmic function, the principal branch is going to be the one where theta is between negative pi and r is greater than 0. So again, remember when I told you that r is equal to 0 is not part of our branch? This is why, because the principal branch does not include 0. The branch cut is a portion of a line or curve that is introduced to define a branch of multiple valued function f. So here the branch cut is this ray at the angle alpha. Points on the branch cut of f are singular points of f, and any point that is common to all branch cuts of f is called a branch point. So the idea is here, here you have one branch and it goes from this ray all the way around. Then your next branch goes from the ray all the way around. So this ray is where you have the common points and is the branch point. And the branch cut for the principal branch of the logarithm consists of the ray theta equals pi. So here you go from negative pi to pi. And another thing to mention is that this ray here, it's dotted because it is not considered part of the branch point, or the branch. Basically because for the branch, the idea is that you want it to be single valued and continuous, whereas you can approach this line both from this positive side and the negative side, and so because you can have different values, you don't want this to be discontinuous. So you do not include this branch cut here. And also you do not include, that's why your branch cuts do not include 0, and r is greater than 0. Next we have this important example. I often don't label things as important because all examples are kind of important, but this one has a surprising result, so I said it's important. So using the principal branch cut, let's evaluate the log of I to the third. So log of I to the third, so I to the third is equal to negative I. And now I want to put this in exponential form. So negative I is down here, so that from the positive x-axis, that's 3 pi over 2. But we want the principal branch cut, which says that theta has to be between negative pi and pi. So this is too large. So we're going to subtract 2 pi. So basically we're going to go around again, but we're going to go the other way around. So we're subtracting 4 pi over 2, or 2 pi. And so that will give us negative pi over 2. So for this branch cut, we're going to represent negative I by e to the negative pi over 2i. So using our log formula now, our log would be the natural log of 1, our radius is 1, minus pi over 2i. Natural log of 1 is 0, so we're left with negative pi over 2. The second of this part of this problem is to compare this to 3 log I. So 3 log I is 3 log, and now I is just here, which is pi over 2, so that's easy. E to the I pi over 2. So we have 3, the radius is 1, natural log of 1, plus I pi over 2. This is 0, and so you're left with I 3 pi over 2. And what is surprising in this example is log of I to the third is not equal to 3 log of I, as it would be if we were in the real numbers. In our overview slide, it is this idea here. And this brings us to identities of logarithms. These two identities are a little surprising because they are not always true when using principal values. That is, the log of the product of z1, z2 is not equal to log of z1 plus log of z2 using principal values. Similarly, log of z1 divided by z2 is not always equal to log of z1 minus log of z2 when using principal values. So I know I have this equality here, but it says it's not always true. So make sure you see that. The next two are similar. Z to the n is equal to e n to the log z, and z to the 1 over n is equal to e 1 over n log z. An example of this here not always being true, let's take z1 and z2 equal to negative 1. So z1 times z2 is equal to 1. So log of 1 is equal to log of e to the 0, which is natural log of 1 because radius is 1, plus I 2 pi n. Remember, this is little l, log. This is 0, so this becomes I 2 pi n. Whereas capital log with the capital L, this n is equal to 0, so we'll have 0. Log of negative 1 is equal to log, radius is 1, e to the I pi is equal to natural log of 1 plus I pi plus I 2 pi n. And this goes to 0, so we have I pi plus I 2 pi n. And so capital log of negative 1 will be equal to I pi. So now if we look at log of z1 times z2, that would be log of 1, which with the capital is equal to 0. And that is not equal to log of z1 plus log of z2. That would be over here, which would be pi I plus pi I. So that would be 2 pi I. So you can see that this is demonstrated. It's not always true when you're using these principal values. To review what we have covered in this video, we started by looking at the logarithm of a complex number, and we derived this equation in a previous video, but we went over and said that when we take the log of z, we write z in the exponential form, r e to the I theta, then we can use the equation that log of z is equal to natural log of r plus I theta plus I 2 pi n. And we said this I 2 pi n made this a multi-valued function. And because later we will be doing things that require a single valued function, we defined the principal log with a capital L of z is equal to natural log of r plus I theta. In other words, we set n is equal to 0 for this principal log. We used this then to define the derivative of logarithms, and we found that the derivation would lead us to 1 over r e to the I theta was just equal to 1 over z, which is the same we would have for real numbers. When we derived the formula for the derivative of the logarithm, first we defined the branch, that is this principal log, so that there was a single value for log z. Again, the importance was that it was single valued, and then we used this theorem here first to show that the log function satisfies the conditions of a function for it to have a derivative at a point z naught. And the two conditions is that the first order partial derivative of the functions exist everywhere. And the second is those partial derivatives are continuous and satisfy the Cauchy-Reimann equation. So we showed that here. And then we get the last part of this theorem tells us that if the derivative exists, that its value is equal to e to the minus I pi u, partial derivative of u with respect to r, plus I, partial derivative of v with respect to r. And this formula was derived when we had looked at this theorem in a previous video. Also, just a note, this u and the v, this is what we have when we break up our function into a real portion and then something times I, the imaginary portion. So for our log function, u is equal to natural log of r, that's our real portion, and v is equal to theta because that's what's multiplied by I. And this is what we used to derive this theorem, this formula here for the log of z. Then we looked further into these idea of branches of logarithm, and again we have these because the logarithm, because it's periodic, is a multi-valued function, but we can get a single value in continuous domain and an analytic function if we made a cut at the ray theta equals alpha. So in this example, here's our ray theta equals alpha is in a dotted line, and what we then say is that our theta that we consider is going to be between alpha and alpha plus 2. So from alpha all the way around to alpha plus 2 pi. So a branch of a multiple valued function f is a single valued function capital F that is analytic in some domain at each point z at which the value f of z is one of the values of f. So in our case, this little f, the multi-valued function here, is like this little log z, and our capital single valued function is like capital log z. And log z has many values for a particular complex number, but our capital log z, or our capital F, has a single value. And the principal branch of the logarithmic function is exactly this capital log of z, natural log of r, plus I theta, where theta goes between negative pi and pi, and r is greater than 0. This is a lot like arg z when we talked about expressing complex numbers in polar coordinates. And then a branch cut is a portion of a line or curve, in this case this is a line, that is introduced in order to define a branch of a multi-valued function f. Points on the branch cut of f are singular points of f, and any point that is common to all branch cuts of f is called a branch point. So in this case, for the principal branch of the logarithm, theta equals pi over here is our branch cut. After that, we looked into different properties of the logarithm, and the first thing we noted is that log I to the n is not equal to n log of I, which is surprising because that's the way it is in real numbers. For our proof, we did this counterexample here where we showed log of I to the third is not equal to 3 log of I. We identified some additional identities of logarithms, which a couple of them are different from what we would expect with real numbers. I now have 4 problems for you to try. The first one is to evaluate log of I on the principal branch. The second is to show log with the capital L of 1 plus I squared is equal to 2 log 1 plus I. The third one is to find all roots of the equation log z equals I times pi over 2. And the last is to show that the set of values for log of I to the 1/2 equals n plus 1 over 4 times pi times I. So I suggest you pause the video, give these problems a try, and when you come back, I'll have solutions. Here are the solutions to the 4 problems. So that's it for this video. Thank you for watching.